This skill module covers heat transfer equipment at the core knowledge level. This section discusses why this topic is important. This skill module covers types of heat exchangers and their common applications. It is important to understand that the transfer of heat is necessary for control of 1. A fluid's temperature and/or its composition and phase, 2. The rate of mass transfer between phases, 3. The rate of chemical reactions, and 4. Temperatures to prevent equipment failure or reduced service life. Heat exchangers normally cost less per unit of energy transferred than any other type of energy equipment. Compromises on exchanger size can significantly increase the cost of companion utility equipment, such as propane refrigeration or hot oil heating utilities. Since heat loads vary with flow rates, some flexibility must be provided. The majority of less than satisfactory exchanger installations are as much the fault of the customer as it is the vendor. Heat transfer in a heat exchanger can be achieved through conduction, convection, radiation, or a combination of these mechanisms. The primary parameters affecting heat transfer coefficients include velocity, pressure drop, fouling, tube diameter, and tube thermal conductivity. The overall heat transfer coefficient plays an important role in sizing, selection, and performance of heat exchangers. Fouling in heat exchangers will reduce the overall heat transfer coefficient and negatively impact heat exchanger performance. Understanding the parameters that affect heat transfer coefficients and how to mitigate fouling conditions are essential for design, selection, and operation of heat exchangers. This module describes how the log mean temperature difference, LMTD, is used to estimate the effective temperature difference to calculate the surface area of a heat exchanger. The minimum temperature approach is an economic choice. As the minimum temperature approach decreases, the effective temperature difference decreases, and the required heat transfer area increases. As the heat transfer area increases, the size and overall cost of the heat exchanger increase. This increase can be significant as the effective temperature difference approaches zero. However, as the temperature approach decreases, the utility costs, power, and fuel decrease because there is better heat transfer efficiency in terms of recovered energy. For example, heat integration, lean-rich amine exchanger, for example, in facilities, can significantly decrease the amount of hot oil required in the amine regenerator reboiler. Both of these effects should be considered in heat exchanger specifications. The heat transfer area required for a heat exchanger is a strong function of the approach temperature selected. The smaller the temperature approach, the greater the surface area required, increasing heat exchanger size and cost. Shell and tube heat exchangers are the workhorse in the oil and gas industry in terms of heat exchangers. Understanding the features, classes, and applications of shell and tube exchangers helps us to select a suitable size and class for our service and have better communications with the vendor and manufacturers. The major considerations for fluid placement are summarized here. Not understanding these considerations, there is a risk of failure, leakage, excessive corrosion, and higher maintenance. Fluids are commonly placed on the shell side. Maximize the heat exchange efficiency of the exchanger design. Provide enough volume surface area for vapor-liquid separation. Provide fluid level control. Provide lower pressure drop. Fluids are often placed on the tube side for better containment and control of toxic and lethal, corrosive, fouling fluids. Safety and environmental consideration. Minimize maintenance. Better fluids mixing like inhibitor injection. These are not mutually exclusive. Some priorities must be established, and some compromises may be necessary. Understanding the advantages and disadvantages for each process cooling method and their applications are important. The choice of process cooling method involves many factors. An intelligent choice involves choosing equipment that optimizes cost of the total system without compromising operating reliability. This skill module discusses the topics shown here. You may also be interested in these gas conditioning and processing principles skill modules.